Start then? Right. Hi everyone, I'm Russell. I'm a senior here at San Jose State studying biomedical engineering.
I'm Catharin, also in biomedical engineering. I'm also a graduating senior.
And our senior project was the Propulsary wheelchair attachment. Just a quick outline of our project. I will take you through the biomedical motivation and the background of our project, basically the inspiration behind it, as well as the FDA considerations, the objectives and deliverables of the project. Catharin will take you through the design of experiments, the methods and results that we were able to gather. Then I will be back to go through the conclusions, cost analysis, and we will conclude with the safety and the future work for our project. So just some quick biomedical motivation for the project. The manual wheelchair industry is incredibly large and is expected to make almost $3 billion this year alone. This includes the sales of manual wheelchairs and the accessories. The manual wheelchair, or the population of users who use only a manual wheelchair is very large. However, only about 17% of wheelchair users actually work. And there's an increasing number of the older population that are being relegated to wheelchairs. So this is some inspiration for us because we want people who are in wheelchairs to be able to get back to work, or we want the older population to be able to operate their wheelchair more efficiently. Because of that, some background to the wheelchair, I'm sure we have all either seen or used them. So you all know how they're traditionally propelled, using like the circular handbar here. You have to pick up and pull yourself forward in like a foot at a time. So because of the mechanical efficiency of a wheelchair is incredibly low, as low as 2% and only about as high as 10%. So this means that only about 10% of the energy that you're actually putting in is actually transferred into forward motion, or backward, depending on which way you're trying to go. So just to summarize that, there's way too much energy required to operate a wheelchair as is now. Because of this, joint pain has been associated with extended use of a manual wheelchair, specifically in the user's wrists, their elbows, and their shoulders, along with muscle pain. The main muscles that have experienced pain are all three of your deltoid muscles, so the anterior, which is in front, the posterior in the back, and the lateral on the side of your shoulder, basically. As well as your biceps, your triceps, and the brachialis, which goes from like here to there. And to alleviate these pains, a lever propulsion mechanism has been proposed as a solution. Some FDA considerations for the device we were able to build is that wheelchairs and their accessories thereof are all class 1. They have minimal risk to them, and they are very safe. So it'd be safe to assume that our device would be a class 1 device. However, there's no predicate for the device that we are trying to build. Therefore, a 510K submission would be required, and because of this, you would need a substantial amount of clinical trials and testing to be able to prove that it is safe and effective. Accessory devices have a relative ease through the FDA process as opposed to their parent device, but this depends on what their parent device is and what it is trying to do for the parent device. As I previously mentioned, ours is an accessory device, and an accessory, as defined by the FDA, is a finished device that is intended to support, supplement, and/or augment the performance of one or more parent devices. And it would be important to state what the device actually does. The FDA has 3 different words that you can see there: support, supplement, and augment. Ours augments the function of a manual wheelchair. This means that it helps the wheelchair to perform its intended use better than before. So that would need to be stated when you are applying for FDA approval, along with a new accessory request. Since the device we built operates differently than the normal wheelchair does, it's not as comparable, so you have to state that it uses different technological characteristics, but it is placed, sorry, I'm forgetting. It's like placed under it, so it's tracked separately, but with that same device, if that makes sense. Here are the regulations for it. Each component to the device would have its own regulation, as well as the overall finished device would have its own regulation. And the manual wheelchairs actually have their own regulations as well. CFR 890.3850, as well as the 510K regulations that would have to be taken into account when applying for FDA approval. So the objective of our senior project was to design, build, and test an attachable device that changes a standard wheelchair's propulsion mechanism from the traditional one to one more of a hand bike. And as well as to verify that the device releases stress and strains on the user's wrist, because that's the whole idea behind using a hand bike sort of motion. The deliverables for our project were the prototype, IRB, application and approval, this would be necessary to do human testing, and you would need a lot of human tests to be able to get clinical trials and to prove the safety and effectiveness of the device, as well as the relative data and analysis that we were able to obtain from our project.
So for our experiment, we wanted to go over basically, we wanted to look at two different types of the wheelchair with and without the attachments. So it's going to be basically the standard wheelchair that we were able to attain with the attachment on and with the attachment off, so that way we have baseline data and data with the device. All the data that we are going to acquire will have a constant heart rate monitoring, and we'll also be having range of motion constantly monitoring also. We also wanted to look at the speed, and we took this by taking the average length that we traveled and the amount of time and calculating the speed from this. So for our first method that we used was heart rate monitoring. We had a chest strap that was the CUSPO HRM H6 chest strap constantly on the subject that was being tested. What this chest strap did, it had a Bluetooth monitor on the front and would send the actual live heart rate to an app on our phone. This is the interface that we were using. Unfortunately, the app we were using wasn't giving us an average heart rate, so what we did is we found the lowest heart rate during a test and the highest heart rate during a test and used the median as an average. The other test we were using was the Biomechanics test, and as you can see, we had sensors from our feet to our heads. We also had shoulders, and we had a sternum and a pelvis. Basically, these are what the sensors look like. They all sync up into a software that is on our laptop, and we were able to use a Wi-Fi adapter to be cordless, completely cordless from anything. And these would show us on the next slide. This is the interface we're using. You can actually see the person being tested on, and if that person were to stand up, move around, it would actually move in the software as the person's moving.
In real time.
In real time, yes. It was very impressive. So for these, we're only looking at 3 of the sensors. We're only looking at the right arm because both of the subjects were right-handed, so we figured that would be the best bet. For the shoulder, we were only looking at flexion and extension, which is this motion, because there wasn't much motion this way or turning. For the wrist joint, we were only looking at ulnar and radial, because again, there's only about this motion, not really this motion or rotation. And then elbow, we were looking at flexion extension. Again, that's the motion we're using. So for baseline, for the heart rate, we found that a male subject typically has a resting heart rate of around the 60 range, and a female will usually have a resting heart rate around the 70 range. Males who are more active have a lower end of the 60, and less active have higher end of the 60, and same with females. So we used pretty much middle for both. So for our subjects, we had them do, our subjects for us, we had us do 2 different runs. Basically, we had a slow run, which was about 2 minutes for each of us, and a fast run, which is about 1.5 minutes for each of us. As you can see, the heart rates dramatically increased on both of our subjects from the low run to the high run. This was just to get a baseline so that in future testing we would be able to compare the amount of energy that we were using on the attachment compared to this. So for biomechanics testing, we again had the same run analyzed for the low intensity and the high intensity. So as you can see, the range of motion on each subject dramatically increased from the low intensity to the high intensity, which makes sense because you're reaching farther back and going farther forward to go faster. Just as a note, the male subject had a lower range of motion, so he probably had more reps, and the female subject had a larger range of motion, so she probably had more reps. As you can see, 113 degrees is a very large range of motion, which could be prone to injury or muscle fatigue, which is what we're going to talk about here. So for baseline testing with just a standard wheelchair, there was a large increase of the heart rate from a low intensity to a high intensity. We also were able to conclude that this heart rate means a lot of work, and the range of motion in conjunction with the heart rate means there's a lot of energy being outputted. This energy, we would assume, and the range of motion could lead to joint and muscle fatigue and possible injury. So that's what we were able to conclude from the baseline testing.
So that's where we started to build our prototype to actually test against it. I really hope you can see back there. So basically going off the sort of hand bike mechanism, we literally had gears and a bike chain attached onto the back wheel. It's fairly simple. We had this stainless steel plate and a smaller gear attached here. We wanted a gear ratio of 2.7. A gear ratio of 2.7. That means that the larger gear in front has 2.7 more teeth than the smaller gear, and this was the optimal gear ratio that we found for acceleration. There are different gear ratios that you can use if you want more speed or more acceleration. This is what we used for getting acceleration. To the front gear mechanism, it's a little more complicated. We had to make a little brace that went onto the frame of the wheelchair, so it drilled into the wheelchair and had the nuts and bolts go through the wheelchair, so it was very stable. And then onto that, we were able to mount a little pillow block bearing here that was held in place with more nuts and bolts. And then to that, we had a little shaft come out, to which we had a shaft collar welded onto, which had holes into it, which had holes on it that were custom to the gear that we were using here. And that gear was screwed on. And we didn't want the gear to be welded because, one, it's chrome, and it's really hard to weld chrome. And also, we just wanted it to be interchangeable, so you could change the gear if you wanted to test a different ratio. And then right here, you can see that we have a PVC pipe. This is just acting as our lever. Eventually, we did change this out for an actual aluminum rod lever, because the PVC actually started to bend and you were losing energy that way. Oops. Unfortunately, the prototype didn't work well enough for us to actually gather good data. It required way too much energy to move yourself. We just had issues with torque. Because you can see right here that the lever is basically just attached with a threaded rod onto this part of the gear, the very inner part of the gear. So there's very little lever arm. So the amount of torque you could generate was very small. And we didn't want to modify the gear in any way because we were worried about the integrity of the gear. We didn't want it to break because we only had 2 of those. So we just didn't want it to break. Along with that, there was this extra metal right here of that was getting in the way, so we had to extend this threaded rod out, and it started to bend as the test was going on. It started to bend just from the torque. And the chain was hitting the U-bolts in the back here, so this steel plate would rotate around, and then the chain would just kind of hit it a little bit. It wasn't significant, but it was enough to be annoying.
So for the cost of the parts, our most expensive part was the pillow block. We found it on McMasterCar.com for about $40 each, so that was very pricey. Our least expensive was the U-bolts. We found most of our parts at Lowe's. We made multiple trips to Lowe's. It was thanks. So then, our welding was free because we were on campus going to Makerspace. They worked with us for probably about a month and a half to 2 months, just going in, getting designs done, doing all of our welding, all of our machining on the metal for us. We didn't have any other option that would be cost effective. In the real world, after university testing, welding services could range from $65 to $125 per hour. And if they supply any of the materials, they can also charge you by the square foot. Other than that, our other fees would be 510K application, as Russell was explaining earlier. I found that for small businesses, which is what we would most likely be, a 510K submission application is about $2,600. If we were in a large business or just anyone else is not considered a small business, it can range up to $10,500. So that's quite expensive. So for safety, as he was explaining earlier, we have a relatively safe device since it is class 1 and is an accessory, not the actual device. But we noticed that with our specific prototype, it was made in haste. So there were a lot of sharp edges and raw unfinished metal. So if you were to reach down and try and move anything and not paying attention, you could potentially cut yourself. With the prototype in future stages, We also noticed that there's a lot of moving parts, like the gears and chains. So again, if you reach your hand down and you touch anywhere in the gear and the chain mechanism, you could get caught and pinched. And there's also possible muscle strain from the lack of torque, just with our specific prototype.
So for the future work, some areas that the design could be improved is just straight up a simpler design. There are way too many small parts that need to be put here and there on the device, so there's way too much precision needed to install it. Like way too much. Like I have fat fingers, I could barely install it, and so I had to get Catharin to do it. And because of this, we wanted to make it easier to attach and detach. Technically, ours is attachable, but it's very hard to get on and off.
Took about half an hour to assemble per
Yeah.
time.
And then also we would like to see different gear settings. Right now we have that one fixed gear setting, but there could be more optimal ones. If you, for some reason, wanted to just go insanely fast on it, there would be a more optimal gear setting for that. And then we would want to enclose the device, just have like some sort of like plastic case around it or something, just so like the gears and the chains aren't exposed so someone doesn't get their finger caught in there for any reason. As for the project, we would like to see that it is continued by another senior project group, because we do believe that our design can work if the torque issue can be figured out. It shouldn't be that hard of a fix, honestly. Also, to test a large number of people, we did obtain IRB approval, and if another group was to take on the future work, they could use our approval and test other people as well, instead of just themselves. Some improvements to design, like I said, could be multiple gear settings and just less small parts. And the main one that we would like to see added to it was the combination of electromyography testing with the body imaging. The body imaging software can be grouped with electromyography, so you can see where the peaks on the EMG and the body mechanics are, so you can see where the person is flexing their shoulder or whatever joint you're looking at, how much energy is actually required for them to be doing that motion. Here are our acknowledgments. We'd like to thank Dr. Matthew Lanoever for all his advice on the project and how to go about building it and everything, as long as Dr. Bruna Salvadori, who helped fund our research, and for all of his reimbursement. I'd like to thank Ian Qualls, Shakabe Tutakil, and Michael Radish, who were last year's senior project team. They gave us a lot of help with the IRB, as well as we used some of their parts from last year, so we'd like to thank them for that. I'd like to thank Dr. Folarin Erogbogbo for his advice for everything this year in senior project, as well as Victor Shaw and Kyle Meininger at Makerspace. They helped a lot with the welding as well as the design. Here are our references. Any questions?
Out of curiosity, why did you put the lever on the furthest gear from the wheel? Did you think about doing the lever at the closest gear, because that is where your hands sit naturally from like a standard wheelchair?
We were trying to reduce the range of motion by putting it back here. You would have to have this range of motion instead of here. So we were just trying to reduce that range of motion. Also, if it was on the small gear in the back, we would have even less amount of torque than the big gear in the front. One thing we considered on the big gear was there were smaller holes on the outside, but we noticed that if we were to put a nut in there, it would obstruct the chain and possibly push the chain off the gear. So this would be something to look into in later prototypes.
And the problem with the torque as well, the top hole is on top of the gear. I can actually go back to it and hopefully you can see it. Maybe?
In that one, yeah.
And this one right here, yeah, you can see here, so like we could have fit a threaded rod through there, and this would actually help with the torque issue. However, this rod was bending under the torque, and we were afraid, because this hole is smaller, so the rod would have to be smaller, that it would also bend under the amount of torque that was required to move yourself.
Can you explain your design?
How so? Like what?
Explain our design.
Yeah, like what is your design?
So this plate here is from last year. We welded on a small gear on the back, and these U-bolts are holding it onto the actual wheelchair. This bike chain is connecting to a larger gear. So in this picture you can see the pillow block. Pillow block is bolted onto a platform that we were able to bolt onto the actual wheelchair. This little shaft in here was shaved down and is screwed into the pillow block. And then there's a collar right here that you can't quite see that's welded onto the shaft and bolted onto the gear. And then there's a threaded rod going through the gear right about here.
So how does it work?
So
you do this sort of motion, So the gear in front moves and it pulls the one in the back and just pulls you forward like you would yourself, like you would normally.
It's similar to a bike combined with like a hand bike kind of elliptical motion. So the lever, ideally, you would push forward and it would push the gear forward, and then you would be able to come back around with the lever, and basically you're controlling this big gear, which is moving the back gear and moving the wheel.
Is it on both sides or is it
Yeah.
on one
Yeah,
side?
it's on both sides.
And we kept them independent of each other so that you can move one without the other, so you could help turn yourself around.
Mhm.
Is the handle connected to the gear in a way that it would kind of be like a crank? Is that
Yes.
so? Like when the gear turns, it would.
Yes.
You're mimicking the gear with the lever arm.
What
Basically.
about when you need to bring your arm back?
How
So
far
you push
back?
forward, right?
So we push forward and down. You're mimicking
Oh,
the
you're
gear.
going-
It comes
You're
around,
going
it
the
comes
whole
around
way.
like this,
Okay.
yeah.
Your hands are basically an extension of the gear.
So, when you pick your gear ratios, well, you found one, I guess, that maximized acceleration was your
Mhm.
goal.
2.7.
Yeah, so you picked that from literature,
From literature, yes.
Okay.
Found on multiple, like, biking
Okay,
websites and stuff.
but then you found out that their size of your gears essentially are too small, because you're not giving you a big enough moment arm?
No, the problem with the moment arm is that the lever right here, that's where the force is coming in, that's pushing on the gear, is super far towards the center, so there's very little torque being generated.
Okay,
So we thought about extending the lever arm. Initially we thought about drilling another hole, but we didn't want to break the gear,
okay,
and there's not a lot of material there to drill a hole
okay.
on.
So you could potentially drill a new hole, but you guys are engineers, right? So you can put some thought into this before you go drilling holes in. So how would you go about for your future, or how would you decide how big that lever arm has to be to produce the torque that you want? Or,
We also thought about another one of the problems that we had. Another problem that we had that we didn't realize before we had already built it is that these gears are really weird and they're not standard at all. So we did have a bigger gear in the box of gears that we were given to work with, and we were thinking about just having it like also on there, because you know how like so if we had a bigger gear, and it's gonna be really hard to explain because I couldn't even explain it to you.
Basically, if we were to have a bigger gear, we would have the chain on the smaller gear, and the bigger gear would allow us to have a larger moment arm. That's kind of where I think you're coming from, is the larger gear would give us a larger moment arm. So then we would use the larger gear to be able to go on the far radius where it already has holes, instead of worrying about the chain on that gear. And then we would bolt the gears together onto the collar of the shaft.
I would say, yeah, I'm just kind of, you guys can, you don't have to guess and check on this, right? You're engineers, you have equations, you can relate torque to power to lever arm, it's all done in there, so.
Yeah.
So I would suggest, for future reference, part of your reports and part of everything is, if you're gonna suggest to do this, give some justification, why what you would do, how you would calculate what torque you need to get in the lever arms and all of that.
Okay.
The other, your range of motion, you reported one number for each, right?
Yeah.
That was the overall, because the software gave you a positive and negative value, because I guess this would be a negative value and this would be a positive value. So we reported that entire range of motion that was being used for the propulsion.
But aren't you really interested in the range of motion per?
So we only did the testing for the baseline without this, because the prototype didn't work well enough where it wasn't.
But even for doing that, aren't you range, like, how consistent, did every time you always grab the same part of the wheel and push forward to the same part of the wheel?
So the way I was analyzing it was I found the largest peak to peak. So on this data you would find like here and here. On the report we'll be finding multiple different peak to peaks and do a standard deviation, but for this simple analysis I found the largest peak. It was completely biased, so that's why I want to change that method for the report. We just found the largest peak to peak and found that range.
So you gave the overall largest range of motion?
Yes.
Yes.
Not range of motion per?
Correct.
No, just the
Okay.
overall.
What is the units on the left?
They're all degrees.
Degrees.
Yeah.
Okay.
This is time and this is degree.
And then I guess the other thing is, you guys your trials did a set distance, set back for
Yeah.
both people, and you
160 meters. So basically,
Just
the
up and
end of
down
this
the hall.
hallway down to the hallway and back is 160 meters.
and you propose an inverse relationship between range of motion and number of repetitions, right? You said you probably did more or shorter.
I would say there's a larger range of motion when there's a larger speed, not necessarily repetitions.
Well, you said that the bigger person that wrestling, he had was it a larger range of motion or a smaller range of motion?
I had
Not
the
as
larger
small.
range.
You had the larger range,
Yes.
so you said over that time, then you probably did fewer turns, right?
Yes. Yeah.
Is there a way you can see that in your data?
Yeah, we can easily calculate that. So each of these peaks is a revolution, so we can just look at those peaks and count those and say how many revolutions there were.
And you can also see where the person turned around right there. That's
Mhm.
where this all went weird.
Yeah, so not a bad, if you think that's an important relationship,
Okay.
maybe just quantify.
Wonderful.
We
All
can
right,
quantify
excellent.
that
Just
too.
count the number of cycles the person needed to do it.
Yeah, everything's important, it'd be
Okay.
interesting to see, yeah.
Okay.
All right, thank you very much.
Thanks, guys.
Me?
Bye.
Thanks, guys.
Thanks, Mom, Dad. Oh,
Just moms.
My mom's.
It's a progressive time.
It's 2018. We don't assume Dr. S.
Priya, are these your final classes? Which are these?
Okay. How many more to go?
Too many.
Yeah, too many.
Dang.
Is this your class?
No.
Three, I don't think you're gonna do one. Sweet. I don't think